All right, let's jump right into this explainer. We're going to explore the invisible, 800,000-mile submerged network that is quite literally the physical heartbeat of our modern world. I want you to imagine a thread of glass, no thicker than a soda straw, resting 3 miles beneath the ocean's surface. It's sitting down there, currently being crushed by the equivalent weight of 1,000 elephants, and yet it is the single reason our digitally connected civilization actually functions today.
There is just this massive, stark contrast between the digital cloud we constantly talk about and the incredibly fragile underwater reality that makes that cloud possible. Up top, we've got buzzing, neon-lit data centers, wireless devices everywhere you look. But right beneath the surface, that whole glowing, futuristic world relies entirely on a solitary, slinky wire plunged into the absolute crushing darkness of the abyssal plain.
Because we're all so used to our smartphones and seamless Wi-Fi, you'd be totally forgiven for thinking your data rains down from satellites floating up in space. It's a super common misconception, but the reality is much more grounded, or I guess submerged. If the ocean floor shifts and these hidden lines snap, civilization basically goes dark. Wireless technology just cannot compete with the sheer volume and speed of data traveling as light through glass across the ocean floor.
So here is the staggering reality. 99% of all international internet traffic runs on nearly 500 active subsea cables crisscrossing the globe. Think about that. From your latest 4K movie stream to family group chats, all the way to incredibly sensitive global financial transactions, 99% of it is literally traveling down a physical transoceanic garden hose resting in the deep sea.
Section 1. Armor for the Abyss. To see exactly how this armor works, let's actually track a single data packet as it leaves a buzzing coastal landing site and plunges straight into the hazardous depths. This is where the sheer engineering of these deep-sea arteries really shines.
When you peel back the layers, you see the crazy amount of armor required to shield a glass core that is, again, basically the width of a soda straw. You've got the brilliant light of the fiber optics right in the absolute center, but it's surrounded by massive, heavy protective layers. The actual part of the cable carrying our traveling data packet is shockingly thin, meaning the vast majority of the cable's bulk is entirely dedicated to defense. To understand how our data survives this descent, we really have to look at the anatomy. These cables typically cost hundreds of millions of dollars, and they require a highly specialized 8-layer protective suit. You've got thixotropic petroleum jelly directly shielding the glass, wrapped in copper, bound in multiple plastic sheaths, and completely encased in high-density polyethylene. Oh, and when the cable is near the shore, where the hazards are actually highest, they slap on this massive heavy steel armoring to the outside.
It is an unbelievable feat of engineering. On one hand, you have a slinky, hair-thin glass wire transmitting up to 400 gigabytes per second. On the other hand, you have the brutal reality of the deep ocean. I mean, at 8,000 meters deep, the water pressure is equal to the weight of 1,000 elephants. The engineering has to perfectly balance maximum data transmission with absolute, impenetrable durability.
Section 2. Powering the light signal. Because, let's be honest, sending a laser across a room is one thing, but making sure your data packet survives a journey across the entire Pacific Ocean without fading into total darkness, that's another beast entirely. To fit all that data down a garden hose-sized channel, engineers use a really sophisticated technique called Dense Wavelength Division Multiplexing, or DWDM. Instead of just sending one beam of light, providers stack multiple wavelengths of light simultaneously through the exact same glass thread. This stacking is the secret sauce that allows for those astonishing speeds of hundreds of gigabytes per second. It creates a blindingly fast digital superhighway for our packets. But here's the catch. Light naturally degrades over distance, even in the purest glass imaginable. To solve this, engineers install physical amplifiers, called repeaters, every 60 to 100 miles along the seabed. These repeaters catch the fading light signal, amplify it, and shoot it forward to the next station. Without them, your data packet would essentially just run out of steam and vanish right in the middle of the Atlantic.
And that fading light, that is exactly why there is a thick layer of copper inside the cable. It carries up to 10,000 volts of direct current electricity to keep those signal-boosting repeaters powered across the ocean. The buzzing landing sites on the coast literally pump high voltage all the way across the seafloor just to make absolutely sure the light never dies out.
Section 3. Surviving deep-sea hazards. So, as our data packet finally reaches the deep abyssal plain, it faces a total barrage of physical and biological threats. The ocean floor, as it turns out, is not a quiet, peaceful place. Believe it or not, human carelessness, like commercial trawler nets and ship anchors, are by far the biggest threats to the network. Because of this, the industry goes to extreme lengths to protect the shallow water sections. Specialized vessels unspool cables at a sedate pace of just 10 kilometers an hour, and behind them, massive underwater plows physically carve deep trenches into the seabed to securely bury the cables totally out of harm's way.
Now, interestingly enough, sharks have historically been caught on video actually nibbling on subsea cables. They're likely attracted by the electromagnetic fields. But modern electromagnetic shielding has largely neutralized that biological threat. So yes, the sharks are still out there, but our protective sheathing now keeps our internet safe from their teeth.
Aside from anchors and marine life, the hazards to our data packet are just intense. Engineers have to spend up to a year mapping routes to actively chart paths around volcanic zones and avoid tectonic shifts. I mean, the 2011 Fukushima earthquake caused major outages. Extreme weather like Hurricane Sandy can knock out coastal nodes. And of course, there is the ever-present geopolitical risk. Nations constantly worry about hostile powers eavesdropping on or deliberately severing these vital lines in acts of gray zone warfare.
Section 4. Big Tech takes control. Okay, let's pivot to the boardroom and see exactly who is footing the massive bill to lay these serpentine superhighways. Because, as you can imagine, dropping a heavily armored 10,000-volt cable across an ocean is an incredibly expensive business.
Right now, we are witnessing a massive shift in who actually owns the internet's physical backbone. Historically, quasi-national telecoms like AT&T and China Telecom totally dominated the space. But modern big tech companies, we're talking Meta, Google, Amazon, they've realized that their future growth is entirely dependent on expanding this physical infrastructure themselves.
Honestly, this corporate takeover makes total logical sense. In the past, cables were often funded by these giant 50-member consortia. The problem? Well, when a cable snaps in the middle of the ocean, nobody in a 50-member group wants to put on a wetsuit and pay to fix it. Today, rather than relying on slow bureaucracies, tech giants are bankrolling massive private networks to fuel their expanding, data-hungry data centers directly.
Take the Maria cable, for example. It links Virginia to Spain, it's 6,600 kilometers long, and it weighs as much as 24 blue whales. It just beautifully showcases the absolute gargantuan scale of this modern private tech infrastructure. The sheer amount of capital required to build a structure that heavy and that wrong is exactly why big tech is now sitting securely at the steering wheel of global connectivity.
Looking toward the future, the scale of this network is only getting bigger. We are looking at sprawling new megacables like the 45,000-kilometer to Africa project and massive Asian routes like the Apricot initiative. But beyond just carrying data, engineers are now integrating sensing technology that will allow these submerged wires to double as massive environmental early warning systems for tsunamis and earthquakes, while also exploring completely new, shorter, transpolar routes through the melting Arctic.
Which leaves us with a final thought to ponder. As low Earth orbit wireless technology, like Starlink, slowly advances and aims to connect the unconnected, will this extreme billion-dollar underwater engineering marvel eventually become just another relic resting in the abyss? Or will the physical, glass and steel arteries of the deep sea remain the undefeated champions of global data? It is definitely something to think about the next time you tap send.